Hi, everybody. Welcome back to Dave's Math channel. I'm your host, David Tare, and this is my sixth video on my series on algebraic number theory. And, I realized that I have to back up a little bit before I continue talking about properties of Gaussian integers, in particular Gaussian primes. There's a lot of results I want to first prove about Gaussian primes, in particular how to classify all of them. But in order to do that, we have to back up a little bit, talk about some more basic concepts, including Euclidean domains and the division algorithm. So anyway, let's begin. Um, first I think I already defined norms. But first let's define an integral domain. So an integral domain is just a particular, sometimes it's just called a domain, but it's a particular type of ring. In particular, it's a ring, we call it D here, and it has no zero divisors. That's the only other characteristic it has. In other words, for every pair of elements A and B in the domain D, if the product AB equals 0, then it's necessarily true that at least one of A or B or possibly both of them is equal to 0. Certainly that's true for the integers, and it's true for the Gaussian integers as well. So those are examples of integral domains, but not every ring is an integral domain. For instance, Z mod 6, 2 times 3 is 0 mod 6. Anyway, we're not going to study those in this lesson. But anyway, so that's what an integral domain is. And once we have an integral domain, we can define a function called a norm on that integral domain. And that's just a function from the domain D to the natural numbers. Here I called it R, I meant to call it D, such that n of 0 is 0, and it's strictly greater than 0. N of A, if A is an element of the integral domain, not 0 element, then its norm has to be greater than 0. So the only element with a norm of 0 is 0 itself. And then also it's multiplicative. So if we have any two elements A, B of D, then it's true that n of A times B is equal to n of A times n of B. And that's even true if one or both of A and B is 0, because 0 times anything is 0. Anyway, so that's what the norm is. And then there's a particular type of integral domain that's very important. It's called a Euclidean domain. And a Euclidean domain, abbreviated as ED, is an integral domain that has a division algorithm on it. In other words, for every pair of elements A and B of your integral domain D, as long as B is non-zero, we can compute the quotient, which we call Q, and we can compute the remainder, R. So in other words, there exist elements Q and R of D such that A equals QB plus R, and in addition, the norm of R is strictly less than the norm of B. And I think you'll note that for the integers, the ordinary integers, this is certainly true, because in this case, if A and B are just ordinary integers with B non-zero, we let the quotient be the floor of the ratio A over B, which is always a rational number. We can take the floor, which is just the largest integer less than or equal to the quotient, the rational quotient A over B, and then we can let R be the remainder upon that division. In other words, A mod B or A modulo B. So I think you can check for yourself or see for yourself that this does satisfy the required condition R. The absolute value of R, well, R is always positive, R non-negative, and R is always less than or equal to the absolute value of B, or the norm of B. So the norm of R, which is just the absolute value of R, is strictly less than the norm of B. And I think you can kind of see this in this picture. I probably should have provided this picture here. So I mean, here you have, they call it D instead of B, but I think you can kind of see what's going on. The remainder belongs to this set, which I guess they call S. It's just all the numbers from 0 to D minus 1. So it is strictly less than D. And we do this all the time when we divide integers. That shouldn't be a mystery. Oh, here's a picture of it. Yeah. So actually, I have another slide where I describe the division algorithm for integers. So we all know how to divide integers. I don't think I have to spend a lot of time on this slide. We just take, like I said, there's a formula for Q as the floor of A over D, and R is the remainder A mod D. So that's all that is. And so now I want to do the same thing. The reason I'm doing all this right now is ultimately we would like to have a division algorithm for the Gaussian integers. That's what I'm leading to. So it turns out the Gaussian integers, not only is that an integral domain, but it's also a Euclidean domain, which means there is a division algorithm for Gaussian integers, and that's what I'm gonna do today. I'm gonna finish up by actually describing a detailed algorithm for computing the for the quotient and a remainder of two given Gaussian integers, where the second one's non-zero. But first, we need a couple definitions. So first, I'm going to define the nearest integer of ordinary real numbers. This shouldn't be anything new. This is just the thing you get when you round a real number. You round up. So in other words, for every real number x, there's an integer which we call x in brackets, round x, I think sometimes people call it. And it's just the unique integer such that the x minus a half is less than round x is less than or equal to x plus a half. We round up, you see. So anyway, but that's what it is. And another way of saying that is that the absolute value of x minus round x is less than or equal to half. It is equal if and only if um, x is an integer plus a half. So anyway, I might have the inequalities switched. I think the left side should be less than or equal to, and the right side should be less than. But I think you get the idea. So anyway, how can we define a nearest Gaussian integer? Well, it's actually pretty easy. We just say, so if z is an ordinary complex number, x plus yi, where x and y are now real numbers, the nearest integer to z, which we write as round z with brackets, the same way we did for real numbers, that's just x with brackets plus y with brackets times I. So in other words, we round the real and imaginary components to get the rounded Gaussian integer, or the nearest Gaussian integer. And so here's a proposition which shows that it is indeed the nearest Gaussian integer. It's the Gaussian integer that's closest to z. I think that's pretty easy. But graphically, it's pretty easy to see. I mean, if you make a graph, here's a little square I drew. So z is this dot that's not in the center of the square. The square is centered at bracket z, the nearest Gaussian integer to z, and there's a little arrow going from that to z, and I think you can see that the length of this arrow, which is the absolute value of z minus z bracket, that is always strictly less than or equal to 1 over the square root of 2, because you're inside a square, and you know that the diagonal, the sides of the square are 1. So the diagonals have length square root of 2. So the farthest it can be from the center is square root of 2 over 2. And you can work it out algebraically as well, which is what I've done here. Anyway, so, and you get equality if and only if the z is minus z bracket is equal to 1 plus I over 2, it turns out. We don't really need that result, but it's true. And anyway, so how can we use this result to come up with a division algorithm for the Gaussian integers? Well, here's the algorithm. First, I'm going to describe the algorithm, and then I'm going to prove that it actually works. It gives us what we want. So the algorithm, this is the division algorithm for Gaussian integers. So our input are two Gaussian integers, alpha and beta. Alpha is a plus bi. Beta is c plus di, which is non-zero, which means that c and d can't both be 0. And then the output is going to be these new Gaussian integers, which I'm calling mu and rho. Mu is m plus ni, and rho is r plus si. Mu is going to be the quotient of a and b, but it's going to be Gaussian integers for the nearest quotient. And rho is going to be the remainder. And we'll see that the norm of rho is strictly less than the norm of beta when we do that. So this is a division algorithm. So that's what we want. How do we get this? Well, it's pretty easy, actually. What we do is we first do the complex quotient, and you can always do that as long as beta is non-zero. So we call z the quotient alpha over beta, and we know we have a formula for how to divide arbitrary complex numbers. It turns out the real component is ac plus bd over c squared plus d squared, and the imaginary component is bc minus AD. I think that should be a minus. Yeah, I put the wrong sign in there. BC minus AD over C squared plus D squared. So that's how we compute it. That's how we compute Z. And then that's step one. But then step two, we have to round Z. So we let mu be Z in brackets, and we have a formula for how to do that. We just find the nearest Gaussian integer to z that we calculated above. And then to get rho, we just take mu times beta minus mu times was it mu times or alpha minus mu times beta, because we want alpha to be mu times beta plus rho. So if we just let rho equal alpha minus mu beta, then we're in business. And another way to write that is z time what is it? Beta times the quantity z minus z bracket. And then finally, to see that this does give us a remainder with a required property, we note that the norm of mu, which we can also write as the absolute value of mu quantity squared, and just using the definition of the absolute value of complex numbers, that's equal to beta, the absolute value of beta squared times the absolute value of z minus z bracket quantity squared, because the absolute value is multiplicative. And but we already proved by the proposition that the absolute value of z minus z bracket is at most 1 over square root of 2. So that means that square is at most 1/2. And that means that the result is at most absolute value of beta quantity squared over 2, which then the absolute value of beta quantity squared is just n of beta, norm of beta. So our result is at most norm of beta over 2, which is strictly less than norm of beta as long as beta is non-zero. And if beta is 0, we don't care, because beta, we started with well, actually, norm of beta will never be 0, because we're assuming beta was non-zero, and the only complex number with a norm of 0 is 0 itself. So that is the proof. So that's the proof that the division algorithm for Gaussian integers works, and we have a specific algorithm for dividing any two Gaussian integers, coming up with a Gaussian quotient and a Gaussian remainder, which is really nice, and we'll find this really useful. In particular, we'll find this useful when we want to work with Gaussian primes. But I thought I'd just finish with a simple example. So let's let alpha here be 3 plus 5i, and beta be 2 plus I. This is a pretty easy example to work with. So first thing we do is we calculate the complex quotient, z equals alpha over beta. And I'm doing it a little bit differently here. This is kind of a trick you'll see a lot. So you write 3 plus 5i over 2 plus I. And a lot of times what you do when you have a complex quotient is you multiply the numerator denominator by the complex conjugate of the denominator of the first fraction. In this case, that's 2 minus I. And then when you do that, you get, in this case, 11, what is it, 11 plus 7i? It's 11 plus 7i over 5, which we can split up into real imaginary parts. Just right, that's 11 fifths plus 7 fifths I, and it's kind of nice we have a denominator of 5 here. We can write these as decimals, terminating decimals. We got 2.2 plus 1.4i. That's the complex quotient. But now what we want to do for step 2, we want to round that, and that's pretty easy to do. Yeah, I think you can see that's 2 plus 1i, or just 2 plus I. That's going to be mu. That's going to be our quotient. And now the remainder is just rho equals alpha minus mu times beta. We just calculate that. You get 3 plus 5i minus 2 plus I quantity squared. Turns out 2 plus I quantity squared is 3 plus 4i. So we're left with 3 plus 5i minus 3 plus 4i. You can group the real and imaginary parts, and you'll just get I when you're done. So our remainder is I. And I think it's pretty easy to see that the norm of I is like, that's 1. And the norm of beta was 5. 2 squared plus 1 squared equals 5. So indeed, the norm of beta is less than the norm, or the norm of rho is indeed less than the norm of beta. So this algorithm worked. It gave us the right quotient and remainder, and we know it's unique by the proposition. So anyway, that completes my video for tonight on the division algorithm, and in particular how to apply it to Gaussian integers. So thank you for watching. Long live math. And by the way, before I get off, I just want to point out this is a different picture on this slide. This slide is actually a graphical representation of the division algorithm for Gaussian integers. I mean, we have two Gaussian integers here, 3 plus 2i and 2 plus 4i, and we're dividing it. And the result, if you round it, is going to be minus I, which is the square, corresponds to the square that the thing. So you can kind of make square. This is a graphical way to divide, complex numbers, and you round it to get the nearest Gaussian integer. And I think I showed this slide on my last video. So now you know what it means. Anyway, thank you for watching. Long live math, and I'll see you guys next time. Bye.